Gianfranco Froyo here. Now get ready to love this stuff. Pharmacology is just playing around with physiology, so we're going to correlate mechanism and side effects of drugs to normal physiology and reinforce core concepts as much as possible. Side effects and mechanism are particularly high yield for step 1, so let's go ahead and get started. Michaelis and Menton were two dudes trying to understand substrates and how they react in the presence of enzyme to make products. They said, okay, sweet, so we have a substance that is a substrate, and it binds to an enzyme to make products. Before that, there's an enzyme substrate complex, and then this enzyme substrate complex will then create products and then regenerate the enzyme. So overall, we have substrates, which are what's going to bind the enzyme, make an enzyme substrate complex, and then make products and then regenerate enzyme. They stared at this and just said, okay, let's make some complicated graphs. Let's make all these graphs, make up some terminology that might be on people's step 1 exams, so we have to know it. Now, Vmax stands for maximum velocity. Maximum velocity is the fastest rate at which you can convert substrate to product when all of your enzymes are in use. In terms of the equation, you have to consider it as Vmax is when all enzyme binding sites are saturated and enzyme exists only in the enzyme substrate complex form. Here we can quickly see that Vmax on the y-axis is where our enzyme has been saturated because there are 0 binding sites left available. For this given concentration of enzyme, Vmax is the fastest rate at which we will be able to convert reactants to products because all the enzyme active binding sites are busy or saturated. Remember, they only exist as enzyme substrate complexes. This is why Vmax is directly proportional to enzyme concentration. How can we increase Vmax? How about you add more enzyme? More enzyme means more active binding sites to bind substrate. Now Km tells us about the affinity of the enzyme for substrate. So Km is affinity. Km is the concentration of substrate at which we reach 1/2 of our Vmax, or maximum velocity. Now the higher the affinity of an enzyme for a substrate, the lower the concentration of the substrate is required to reach Vmax. So low Km, it's high affinity, and low amount of substrate required. If the substrate and enzyme love each other, then you just don't need that high of a concentration of either one to form a lot of enzyme substrate complexes. Remember that when all enzyme is bound to a substrate, this is our Vmax. Everything is saturated. So a low Km means that we reach 1/2 of Vmax at a lower concentration of substrate. On the other hand, a high Km means that we have decreased affinity and therefore we need a higher concentration of substrate. You must have a higher concentration of substrate because the enzyme really just isn't that interested in making enzyme substrate complexes. Notice the hyperbolic curve of the graph. This tells us that the velocity initially increases really fast, exponentially, and then it kind of just tapers off as less and less free enzymes are available to participate in new enzyme substrate complexes. Remember, this is the big deal when thinking about Vmax, Km, and affinity. This emphasizes the important concept that Vmax is directly proportional to the amount of enzyme. If more enzymes are added, then the Vmax to the reaction will increase. The second graph is the Lineweaver-Burke plot. This is conceptual. No one makes these anymore now that we have computers, but it is a perfect graph to test your understanding of enzyme kinetics and terminology. It is also known as a double reciprocal plot because it literally takes the terms from the Michaelis-Menten graph and inverts them to the reciprocal. Let's check this out. Here we have these are a reciprocal of Km, so 1 divided by Km, and this is our x-intercept. Also here we have 1 divided by Vmax, which is the reciprocal of Vmax. This is our y-intercept. This all seems rather worthless until you get a question on the test and you have no idea what's going on. You'll probably get a question where they show you this graph and ask you to interpret something based on it. Remember that Km represents affinity, right? And it is equal to the substrate concentration at 1/2 of Vmax. So for example, let's say that we have a high Km like 100. We plug that into the graph, and we can see that 1 divided by 100 will shift this x-intercept to the right, because 1 divided by 100 is very close to 0.01. Focus in here. This is actually important. Unlike the last two graphs, they're just test questions. This actually has something to do with real medicine. Now, we use the word compete because the question is, will the inhibitor directly compete with the substrate at the same active binding site on the enzyme, making it a competitive inhibitor, or will the inhibitor bind to another completely different location, making it a non-competitive inhibitor? Competitive inhibitors can reversibly or irreversibly bind at the same active binding site on the enzyme. We need to go more in depth here because this will be on your board exams. So let's draw this. So here we have quickly drawn an enzyme represented by E. It looks like Pac-Man with an active binding site shaped like a V. So this is our active binding site. And the non-competitive inhibitor binding site shaped like a square. Notice how the non-competitive inhibitor does not resemble the substrate. The substrate looks like a triangle that fits into the active binding site. When a non-competitive inhibitor binds here in this location, different from the active binding site, the enzyme's overall conformation is changed, and it will lock into a new overall shape that looks something like this. So this is the non-competitor now in position. Notice how the substrate active binding site still looks the same and even has the substrate engaged. It can easily bind the substrate. Because the active binding site and the substrate still have the same affinity, because they can still bind each other, the Km is unchanged. So again, non-competitive inhibitors do not resemble substrate and therefore do not bind the active binding site. They bind here and they can still affect the overall chemical reaction. So here let's look at this graph. What will happen to Vmax with a non-competitive inhibitor? The overall new conformation of the enzyme with the non-competitive inhibitor attached is going to hinder the overall reaction from occurring because the enzyme cannot rearrange itself in a way to carry out the chemical reaction. This is that enzymatic activity is decreased. So this drops the Vmax because the reaction cannot be carried out at the same velocity when the enzyme is locked into place by the non-competitive inhibitor. This effect cannot be overcome by adding more substrate. This does nothing because the non-competitive inhibitor is directly messing with the enzyme's ability to change its shape to carry out the reaction. Okay, now with the Lineweaver-Burke plot. In comparison to the uninhibited enzyme, why do you think the non-competitive inhibitor changes the y-intercept but does not change the x-intercept? Remember that the y-intercept represents 1 divided by Vmax, and the x-intercept is 1 divided by negative Km. Non-competitive inhibitors do not change the affinity of the enzyme active site for substrate, so there's no reason for the Km or the x-intercept to change. These stay the same. But the y-intercept shifts up the axis because the number in the denominator severely decreases because Vmax drops. So if you divide by a smaller number, then you shift up the y-axis. Okay, now what happens in competitive inhibitors? Here we go with a better diagram. Competitive inhibitors directly compete with the substrate at the active binding site. This is the inhibitor, and then this is the substrate. This is because they usually resemble or share similar properties to the substrate that normally fits in there. We further classify the competitive inhibitors into reversible or irreversible. Now, reversible inhibitors transiently compete with the substrate for the binding site and can be displaced if you just increase the concentration of your substrate. This means you can still reach Vmax, but you just need more substrate to knock the reversible competitor away from the active binding site. So you add more of this, increased chances it competes with the inhibitor. Remember, Vmax is dependent on the amount of available enzyme binding sites. So it doesn't really care that much about the substrate concentration. Vmax again does not change because the competitor can be displaced if you just increase the concentration of substrate. You can still get to the same velocity, you just need more fuel. Now Km is going to increase because the competing molecule interferes with the affinity of the enzyme for the substrate. Again, affinity. So now we have to give a higher dose of substrate or drug. This means that now our drug is less potent because we have to give more of it. You have to deliver more because you need a higher concentration in order to reach the same Vmax. So let's look at our reversible competitive inhibitors graphically, because this is how you're going to be tested and this stuff can get confusing. Do you see here how Vmax will reach the same value, but we just need a higher concentration of substrate going up the competitive inhibitor line? And if we draw Km at 1/2 of Vmax for the competitive inhibitor line, it confirms what we know about Km and the fact that it will increase in the presence of a competitive reversible inhibitor. Let's quickly discuss irreversible competitive inhibitors. An irreversible inhibitor resembles substrate and forms an irreversible covalent bond directly with the enzyme's active binding site. The prime example is how organophosphates latch on to the acetylcholinesterase enzyme. They render this enzyme useless forever. You can't get to the active binding site anymore unless you give pralidoxime within the hour. That's just a side point. If you don't give pralidoxime, then you permanently lose this enzyme. This will actually drop Vmax because we have lost available enzyme binding sites completely. There is no effect on Km though. Why does Km stay the same? This is because the remaining enzymes that were not denatured because they were not bound by organophosphate are still available and they can still bind substrate. So the enzymes that are still there have the same affinity for the substrate. Pharmacokinetics is what the body does to the drug. Bioavailability is represented by an F because it's the fraction of an administered drug that actually reaches the plasma in circulation. If you put a drug directly into the patient's blood, such as intravenous drug administration, that's 100% bioavailable because it's going straight in there. Now, PO, or oral administration, is different because of the first pass hepatic metabolism. Everything has to go through the liver, right? Anything that is absorbed through the intestine is taken to the liver via the portal venous system so that the liver can attempt to detoxify and inspect drugs first. It's like security at the airport. No exceptions, you gotta go through there. Some of the drug is lost to this first pass hepatic metabolism, which means that oral administration of the drug makes bioavailability less than 100% by default. Volume of distribution compares the amount of drug in the plasma to the total amount that's actually in the body completely. When trying to understand volume of distribution, you should think about the fluid compartments in the body. And you should also think about the polarity and the size of whatever drug we're talking about. The fluid compartments that compose the theoretical 42 liters of total body water mean that we're talking about the ICF, which is what total percent of body water? 66%, or 2/3. So that's pretty big, right? That's 28 liters, and the ECF is the remaining 14 liters. Remember, the ECF is further divided into 3 liters of plasma, blood volume, and 11 liters of interstitial fluid. So let's look at our equation. This is amount of drug in the body divided by the amount of drug in the plasma. This means that the dose we gave the patient can potentially be distributed anywhere in the body. So we divide this number by the concentration of the drug that is only found in the 3 liters of plasma volume. So basically the question I like to ask myself is, what properties of the drug will make it remain just in the plasma or distribute into the other parts of the body? Not just the water components, but even the fat tissues. The only part of the equation we truly care about is the denominator. If the plasma drug concentration is low, then the denominator is a small number and the calculation gives us a high volume of distribution. So let's consider a drug that is said to have a high volume of distribution. So drugs with high volume of distribution easily escape the plasma, they slip out, and therefore they drop the plasma concentration. Why? Well, molecules that escape the plasma are small and fat-loving lipophilic molecules. They easily slide across cell membranes and can distribute within cells anywhere. This means that they have high intracellular concentrations. An important example is THC. This is a molecule in marijuana that gets users feeling nice and high and baked. It's very small. It's a very lipophilic molecule. Therefore, it can be distributed widely throughout the body, and it particularly loves to be stored within fat adipocytes, right? This is where it is slowly going to be metabolized for long periods of time. This is why we do a urine drug screen. We can pick up this drug for days to weeks depending on how much it is used and the percent body fat of the patient. So if you're trying to pass a drug test, get on that treadmill and burn that fat. On the opposite end of the spectrum, a very large and polar or charged molecule like heparin, it loves to bind plasma proteins. It cannot cross cell membranes, and it likes to hang out in the plasma. Its plasma concentration is pretty high, and therefore, if a high denominator value gives us a low volume of distribution. This is only like 3.5 liters, remember? So it has a very low volume of distribution because it's staying in the plasma. It does not distribute into other compartments of the body where a majority of the volume is. Now in the middle, you have a medium value of volume distribution. This is usually a drug that is small, but it likes water. A hydrophilic molecule. It can basically hang out anywhere in the ECF. So this ECF is a fairly large compartment, but nothing like a drug that can enter into cells and distribute within fat. Of course, we have to have another equation. Now, clearance is the volume of plasma that is cleared or cleansed of a drug in a given amount of time. So here's our equation. Notice how it looks just like volume of distribution, except that we have switched out the numerator for rate of elimination. This is why we can say that it is equivalent to the volume of distribution times a constant, Ke. That is the elimination rate constant. Clearance in the human body is mainly dependent on hepatic or renal function. Most drugs that we give people have a constant clearance, which means that the rate of drug elimination is directly proportional to the concentration of the drug that is inside of the patient. This is called first order elimination. We'll get into this in a second. So half-life should be thought of as the time required to reach 50% of the current concentration, or the time for 50% of the drug to be cleared from the body, which again is usually through renal or hepatic clearance. The way this whole half-life thing works is just in percentages. For example, let's say that we are giving the patient fosphenytoin for new onset seizures, and we're giving them IV, which is the only way you can give it, and it's converted into phenytoin in the body in about 15 minutes, and then this whole thing stays in the body for about 12 to 28 hours, and let's just say one half-life is 12 hours, because just keep our brains alive and not killing the brain cells. So that one half-life, or 12 hours, we can expect 50% of this intravenous infusion of fosphenytoin, which is converted into phenytoin, to be in the person's body. So that in 24 hours, or the second half-life, we get 75% of the drug that we want in there, followed by 36 hours, we have 87.5%, 48 hours, reaching 93.75%, and then the last half-life at 60 hours at 96.875%. I mean, obviously we don't need to write all this out, but it's important to just kind of get a feeling of this because I think about this all the time when I'm giving a patient a drug. So around here, around 5 half-lives, we have reached steady state. But all of a sudden, our attending finds out that the person doesn't have insurance, and then he pulls out the IV and says, "You're done." Stops giving the drug to the patient. The patient says, "Oh no, doc. As soon as most of that phenytoin is out of my system, I'm going to have a seizure, aren't I?" The patient wants to know how long this will be. Well, you say, "Sir, we just painfully wrote all this out on the slide, right? We reached steady state in 60 hours or 5 half-lives. So it'll be the same number of half-lives to eliminate the drug as it did to reach the steady state. So you tell the patient, "Dude, you're going to be okay for 60 hours, and then around then you might have a seizure. So enjoy those 60 hours, man." I'm just kidding, that would never happen, but this is how you have to think about things so they're memorable and you're going to learn. So I just approximate this and say that around 3.3 half-lives, like this is a 90%, that's a pretty decent amount of drug that we expect to get in the body. I've never seen you to ask to calculate the question, but you need to memorize it just in case because they're easy points. The equation is half-life is equal to 0.693 times the volume of distribution divided by the clearance. And again, this is only useful for first-order elimination. These equations will probably not show up on your exam considering we are physicians, not pharmacists, but you still have to understand the concepts because we work with pharmacists all the time. Now the loading dose tells us how much of a drug we need to give to reach the target plasma concentration. So CP is target plasma concentration, and this is what we want to get. Why are we multiplying by the volume of distribution? Remember, a higher volume of distribution means that we need to give more drug to cover this large area that the drug will distribute in. So a larger loading dose is needed. Why are we dividing by bioavailability? Well, not all drugs enter the plasma at the same dose we gave them. Everything taken orally or PO must first pass by the liver, and we might lose some of the drug to the hepatic first pass metabolism. The maintenance dose is the exact same equation basically, except that we switch out volume of distribution for the clearance, and then we multiply by this fancy T called the tau. Why? Well, now we're worried about maintaining a certain plasma concentration, not establishing one. In order to maintain a certain concentration, we have to take into the account the rate at which the kidneys and liver are eliminating the drug or clearing it from a given volume of plasma. Now, if someone has renal or hepatic disease, the maintenance dose decreases because the renal and hepatic clearance is lower. Therefore, this value will be smaller in our calculation and will drop the overall number. Now, this fancy tau protein represents the dosage interval, which is simply the time between doses that you need to consider when giving a patient a drug. And this is if you're not infusing the drug at a constant rate. If there is a large time interval between doses, then that directly translates into a larger maintenance dose.